I'm Ryan Michael. I work at this project called Kaskada. It's an open source library we were acquired by DataStax, so that's kind of like my background. So what I want to talk about today is kind of this idea of real-time generative AI. We've seen a lot of really cool examples, but one of the things that I think a lot of the stuff that's coming out lately has in common is that it's sort of an AI that waits for you to ask it a question and then it gives you a response. And I think that there's space in the kind of technical sphere to do something more interactive and build applications that are kind of looking for opportunities to be helpful. Interactivity and kind of being able to watch what's happening as it happens and react in real time. And to kind of show what I think are some of the opportunities here, we built this example application. We call it BeepGPT. And it's a Slack bot. What it does is it's been trained to understand what everyone in your Slack organization is interested in, what they're good at, what they tend to talk about, who they interact with. And it just watches what's happening in Slack. And when it sees something that it thinks you would be interested in, it lets you know. It's just like, hey, you should probably pay attention to this conversation. So just kind of simple example. This is an example of Preeti. She's a PM that works with us. She's leaving a message that says, hey, we're launching a new marketing campaign. I'm finalizing the requirements. And this is something I would want to be a part of this conversation. I have opinions. So BeepGPT has learned that I tend to interact with conversations like this. And it lets me know. It's like, hey, there's a conversation going on right now. You should go participate. And so what we're seeing here is that we're using these LLMs to observe what's happening in real time and give me an opportunity to engage in this conversation that I might not have been able to engage in if I was just, doing my stuff. We thought about calling this the FOMO 2000 or something. But the goal here is to make it so that you can focus on what you actually care about and kind of only give you notifications when it's relevant. So this would have been a very difficult application to build just a year ago, right? And there's a couple of really important changes that have made this possible now. And I'm going to just kind of high level what we kind of see as the big enabling factors here. The first are these foundation models. These are giant models created by Google, OpenAI, Anthropic. And what matters about these models is that they reduce the data set that you need to bring to a problem because they've learned so much about the world. They're able to much more rapidly figure out what you're asking them for. The second big thing is AI as a service. So a lot of these companies, Google, OpenAI, they made it really easy to just hit their API and fine tune or do inference. You don't have to be an expert. You don't have to have a bunch of infrastructure. Use their APIs, pay for it. You're good to go. It makes it much easier to get started. And then the final thing, which is what I'm going to focus on here because it's what I work on, is the ability to connect real-time data to these generative AI applications and kind of interact with the world as things are happening in an intelligent way. So let me kind of walk through how we implemented this. So the first thing we did was we fine-tuned a model so we could have our custom LLM. This is how we trained it, what everyone was interested in, what everyone needed to be a part of. But obviously it's more complex than that. We did this by starting with the Slack historical data from our entire organization. So this is really easy to get with Slack's API. You just click a button, it'll give you a full download of all of your data. We use that to construct historical prompts. So what would we have asked the model during the conversations as they unfolded in the past? And we use that as our fine-tuning training data set. The second step was to actually consume events as they occur in Slack and construct the same analogous prompts to give to the LLM. This allowed us to get feedback from the LLM and make a decision about, do I need to notify somebody right now and who? So this is the sort of process diagram here. I've got some magic balls in here because there's some parts of this that are kind of difficult. So let's kind of talk about what's hard about this process. What was difficult originally and what do we think is easier now? The first thing is that we have to do both of these different analyses over different shapes of data. The historical analysis that we use to fine-tune the model is happening over a large data set that we want to do a once and done analysis on. Whereas to do this in real time, we're getting single events. Now, traditionally, this would require different tooling and different kind of approaches to the problem. This is one stumbling block. The second is that we can't just look at a single event. We couldn't set up like a Lambda handler and just process each message as it comes in, because we need context. We need to understand the conversation over the past 10 or 20 minutes to be able to actually understand what matters. So we need to be able to aggregate. We need to be able to provide a rich context to the model. And then the final thing is that the traditional tools that have been used to solve this type of real-time data processing have often been infrastructure heavy because they were developed by LinkedIn or Google. And so you'd spend the first month or so just setting up Kafka clusters and scaling and all that kind of stuff. And so there's a large barrier to entry to be able to just get started quickly. So we built Kaskada to solve these problems specifically. And I want to talk about how we solve that. But before we do that, I want to take a brief detour and kind of just talk about data processing. So I promise I'll get back to AI in just a second, but I want to take a brief detour here. So there's kind of two high-level ways of processing data. You can do it as a batch, or you can do it as a stream. Batch data processing we're all familiar with. You've got some rows in a table. You apply some operation here. It's a sum. You get an answer, right? This is very easy to understand. And we've been doing this since the 70s. So there's lots of really good optimizations. If we process these from a columnar data source, we can make good use of CPU caching, memory usage. All that stuff is highly optimized to make this really good. And so we can do this at high throughput. We can process lots of data. This is the problem, though, is that what happens when you add another row? We have to recompute the whole data set. All of this stuff in the dotted line, we just wasted. We didn't need to do that. We could take the previous answer and just add 10 to it. And so what this means is that updating your computations as data arrives using a batch data processing mechanism is really expensive. So what we see as stream data processing emerges to kind of take this intuition and run with it, right? Well, we can just add 10. So what we can do instead is we can take that same data set and we can process it one value at a time. And each step will take the result of the previous operation, add the new value. When we get a new value, we just play this forward, right? This is just a simple, consistent process that we push through time. This is really cheap to update, which means that we can do this at really low latency. We can process data really quickly. But this has downsides as well. So the biggest downside is that this, for most people, is hard to think about and reason about. This can be really difficult to wrap your head around and write the software that does this. And it's also traditionally been difficult to implement. Just the state management and the kind of dealing with the data as it arrives is often not super easy to implement yourself. And so we built Kaskada to solve kind of the problems of dealing with real-time data by taking the strengths of both of these approaches, both the sort of bulk data processing from batch world and the kind of incremental real-time processing from streaming. And we started by addressing this hard to understand problem. So what we did was we began by developing a new set of ways of thinking about how you describe a computation. We've built our system on top of this idea of a timeline. So a timeline is kind of what you would imagine. It's what we were looking at. You have a series of values that happen at different points in time. You can lay them out with time on the horizontal axis and then do operations on them. In this case, we're going to compute the sum. So as you can see, when we operate on these values, we start with a timeline and we end with a timeline. We always preserve this time axis. We can do more interesting things. So we can do windowed aggregations, reset the aggregation at the beginning of the month. We can do aggregations that are relative to different types of events. So in this case, we're counting how many times somebody views our page since the last time they purchased something. I'm not going to go into all the details of this, but suffice to say that we've built a really rich operational language that lets you describe everything you would want to do in a way that preserves the time axis. And what this means is that if you describe your computations using these operations, we can do both the historical and the real-time analysis transparently. Now, I've got some animation here. And so this is kind of where Kaskada fits into this process. Because we have this unifying abstraction between the batch and the stream world, you can handle both of those types of data without rewriting anything. You take your computation description that you use to timelines to build, you hand it off to our library, you can process different types of data. You can do that either in a batch where you just say, give me the historical analysis right now, I'm going to build fine-tuning examples, or run this continuously as new data arrives. And Kaskada takes care of all the state management. So this is addressing some of the complexity of operationalizing these. And so this is kind of our solution to these problems, right? We have the ability to do historical replay that allows you to unify historic and real-time processing. We have these time stream or timeline-based abstract operations that make it much easier to do aggregation and context analysis or context construction. And because this is all just packaged in a Python library that you can just get started with, you, in many cases, don't need to worry about infrastructure. You can just start handling data as it arrives. And so this is kind of where Kaskada fits in this, is that both of these analyses are able to reuse the code that we're doing to drive both the fine-tuning and the live application. So let's take a look at what this actually looks like. This is a subset of the code. The full thing is available on GitHub. I'll have a link to it in just a second. But at a high level, what we're going to do is start by building the conversation. We're aggregating across all the events so that we can build the input to our model. In this case, we're going to just select some fields and then collect 20 consecutive ones. This is a very simple aggregation. Before we can hand this to the model, we need to do a little bit of formatting to it. So we need to apply padding and join different messages and whatnot. So we've got a UDF here that we can use to do that. We could also apply embedding models, use whatever kind of scikit-learn preprocessing you would want to use. All that's available as UDFs. And then finally, we just build our training example. Our training example consists of a prompt and the completion. The prompt in this case would be the state of the conversation at a particular point in time, and the completion would be who is interested in the conversation. We'll talk a little bit about what that means in a sec. This is really all that we need to build the fine-tuned model. And so now we can move into the what do we do in real time. So in this example, we're just relying on the Slack API. Slack has a WebSocket API. They'll send you events as they happen, and we can just process them one at a time. The only line in here that's actually specific to Kaskada is this one that I've highlighted in orange. We're just adding the row. We're saying, we received a message, we did some formatting, add this to the data that you're aware of, and that gets folded into that accumulation that we built. From there, we're ready to start consuming the results. Kaskada's asynchronously computing outputs as we're putting data into it. And so here we're just setting up a handler that says every time there's a new output, every time there's a new conversation that's created or a new result from our operation, handle it with this block. And what we're doing with it is just, looking to see whether the person that are predicted are sufficiently interested in the conversation. We can get into details maybe after the talk, and send notifications to the people that are actually engaged. The whole code base is on here, so if you're actually interested, feel free to take a look, train this on your own Slack workspace if you're interested. I'd love to hear how it works for you. And this was kind of the starting point. We went through a series of iterations, fine-tuning and improving on this model. We looked at different ways of extracting how do you know if someone's interested in a conversation? Is it because they replied or because they engaged with the message by, adding an emoji or something? And then how do we build that context, right? Do we need like the most recent messages? Do we want to thread them in different ways, whatnot? And so there's a series of notebooks in there where we kind of look at different operations. So if you're interested in kind of looking at how you would build this type of fine-tuning data set, that's there. This QR code actually goes to a full write-up that one of the engineers that worked on this did, kind of talking through his process and really getting into the lessons that he learned working with the OpenAI APIs. It's a pretty good blog post. So at a very high level, let me just kind of summarize what we kind of learned through this process on the actual generative AI front. The first one is that LLMs aren't just for generating. That's not the only thing they're good at. They're actually really good at understanding. Before they can respond to you, they have to understand what you asked. And that's an incredibly powerful capability, which I think is overlooked in many cases. Just being able to observe the world intelligently, there's a lot of interesting applications of that. Second thing is that fine-tuning is really powerful. I think that there's been a lot of back and forth between prompt engineering versus fine tuning. There are many problems that are just better suited for fine tuning. We would not have been able to solve this problem easily. We're with like RAG. We're trying right now. We're doing a version of this that uses RAG and kind of uses nearest neighbor search to try to figure out whether we can solve this problem the same way. But it was so easy to just fine tune. We just kind of built some examples and threw it at the model, and we got a working model. And so for certain problems, fine tuning is a great solution. The other thing is that there's a lot of real-time data out there. We've built demos for Slack, Reddit, Blue Sky. I'm sure there's more. We don't have an exhaustive list right now, but there's a lot of sources of data out there that you can consume that give you an understanding of what's happening in real time, and don't require any infrastructure. And then the last thing, there's a lot more information about this in that blog post, but one of the tricks we discovered is that LLMs are really good at improving the data quality of the training data set that you're giving it. The first version of this wasn't very performant. And so we had the LLM go through and just segment our data set into like interesting and not interesting messages. And then we only trained on the interesting ones. And so we got much better performance by just having the LLM kind of participate in its own process. So I kind of started this by talking about opportunities. I don't know what all we can do with this, but I think that there's a really interesting kind of landscape that we can explore here, where we start looking at what we can do in real time, what we can do with models that are helping us proactively, models that we don't tell exactly what we want to do, we just tell it what we want them to optimize, and then they find opportunities to make that happen. So I would encourage you all to think about this, and hopefully use Kaskada to solve those problems. So this is a QR code for our Slack. We are an open source project. The library is free to download and use. We would love to hear about what you're working on. I would love to hear about what you're working on. If you have any questions about use cases or kind of patterns we're seeing in the market, I'll be here after the talk, obviously, but also feel free to join our Slack. There's a URL here for the actual BeepGPT implementation. Yeah, that's what I've got. The kind of like relevance of good data, I think, is definitely increasing more and more. I think one of the things that the newer models are unlocking is that it's making a lot more types of data available to be good data. You don't have to necessarily just throw a bunch of volume at it. You can oftentimes have better analysis rather than better volumes of data. And I think that's what Kaskada is really focusing on, is kind of making it easy to be able to get the data into a form that you can analyze it with these models. A lot of the interesting developments in database design around vector storage and scalability and things like that, I think, are allowing us to use this information in new ways, which I think is really exciting. So I think vector indexing is got a lot of interesting applications. Yeah, it looks like you've got a follow-up. I guess my feeling is that what we're starting to see is that vector indexing is a feature that most databases are likely going to, if they have not already rolled out, will have within the next couple of months. This is an important use case, and I don't think anybody that has a database is not going to support vector indexing pretty soon. And so I think what this ends up meaning is that in many cases, vector or databases generally start to kind of return to their strengths. So you'll probably see graph databases with vector. You'll probably see document databases with vector. You'll probably see, local databases with vector. And so I think the question in many ways is like, what is the most appropriate way of storing data for your use case? And if you have, a use case that depends on enterprise scalability and, reliable uptime, Cassandra is a great way of doing that. If you're, working on other problems, there might be other solutions. But I think this has quickly become table stakes for data storage. I will say this is not something that I focus on. So this is kind of like unvarnished opinions. So this is the kind of cold start problem. We have not implemented a solution to that. We've talked about a number of different options. So this is where I think the vector store that we were talking about potentially comes into play. So you could do things like embed information about each user. What department are they part of? What is their background? What is their sort of, specialties? What do they know about? And use that as part of the solution, right? So you could provide some context around what is the state of the conversation right now? Are we talking about, one technical field or another, and use that to kind of do vector retrieval to find all the people whose profiles are similar to the current state of the conversation, and then provide that as additional context. So I think that's one opportunity. The other is to just kind of train continuously. So our model was performed well with 2,000 examples, basically. We were measuring with F1 scores, if we're going to get into the kind of details. But we don't actually need a whole lot of data in a lot of cases. It kind of depends on, how many people you would have in the organization, how varied the things are. I think the model will be able to key on certain things more easily than others. But I think that, the way that it's implemented right now, it is learning from the actual interactions of the users. And so you would need to absorb some of that. So there's no quick fix to that aside from just kind of bringing in other information like demographic or, background resume type information. So I think there's a lot of different places you could get data from. So we're working on an example right now, actually, of kind of pulling in data from Reddit subthreads about NFTs and stock market type stuff and correlating that against price movement to try to build a model that would predict some of that.
So it supports it.
Yeah. So the library kind of has a couple of different ways it can source data, but one of them is that you just pass it some rows, as we saw right there. So if you can pull the data into Python, you can hand it to Kaskada and we can compute over it, basically. So, that could be stock tickers, that could be news articles, that could be social media posts, that could be your Twitter feed, whatever. Wherever you can get data from, you shove it in and we can process it. No, so internally, the compute engine itself is basically just a really optimized Rust-based implementation. So we can process millions of rows a second in historical mode. We don't actually call out to models ourselves. Okay. So we're just a tool to kind of connect the data from where it's coming in to the form that it would be in to be able to provide it to a model. And then you could write a UDF to basically say okay, every time there's a new conversation, I want you to send that to OpenAI and get a response back. But we don't do any of that automatically. We're just a data processing tool that simplifies the flows of information. We're not using the chat interface to OpenAI. We're building all of the context ourselves and just passing it in as a single query. We're actually using the completion API rather than the chat API. It's pretty cheap, really. We trained the model for a couple of bucks. This was not our entire training cost because we iterated and then we tried some more expensive models and some cheaper models. So we ended up spending a couple $100s on this end to end. But yeah, you could train this for, an amount of money that you wouldn't bat your eyes at. And our average message size was about a quarter penny per message, in our Slack data. So, what that means is that multiply that by how many messages your organization is sending. And, this is an expensive model, compared to what you would do if you were running this on a old school predictive model. This is insanely expensive. But for something like this, where you're solving problems that are sort of human timescale, it's not that bad, really. So, it's up to you. Maybe you don't get a quarter penny of value out of it. It's certainly possible, but it's not insanely expensive.